Now let's consider the electric field. So we have, say, a uniformly charged object, positively charged. It will produce an electric field in three-dimensional space. Obviously, a two-dimensional slice is shown here. The strength of the electric field graphically is related to the spacing between the lines, so it's getting less because it's diverging as we go out further in space. And the direction of the electric field is given by the vector direction shown here. Now, if we put a positive test charge at a point charge P, actually Q0 at point P, there is an electric field that this charge is subjected to. And electric fields produce forces on charges. In fact, if a force exists, a field exists. Now, that's not a logically essential statement. It is not true by logical deduction. It's an empirical result. We never see a non-gravitational effect on a charge, a force, a non-gravitational force on a charge, apart from a field being there. So we can safely assume that they're related. Now, this is showing the direction of the electric force in this charge. And notice that the direction of the electric force is the same as the direction of the electric field at this point. Now, the electric field is equal to, quantitatively, the force divided by the charge. So it's force per charge. That is the essential definition of electric field intensity. So the electric force itself is QE, charge times field. Now, actually, a little more carefully, this is a small detail, but probably worth mentioning. The E field is the limit of force per charge as the charge approaches zero. And there's a reason for the limit being of interesting conceptual note here, at least. Why only for point charges? And the reason is because this charge will actually redistribute the charge of the source. So if this is a positive charge, it's going to push on these charges, redistribute them, and now you have a different geometry of charge distribution, which results in a different electric field geometric distribution. So the charges will redistribute geometrically. All right, so for the most part, we don't have to worry about that. Now, an analogy to this definition of electric field is the gravitational field. So electric field is force per charge. Gravitational field is force per mass. Fg is equal to mg, or g is Fg over m. So they're very closely tied. Good analogy. Now, if Q0 is positive, the test charge that is in this field is positive, the force and electric field are in the same direction. On the other hand, if the charge is negative, the force and field are in the opposite direction. Superposition of charge is just a simple vector consideration. Namely, here we have a negative charge. And over here is a positive charge. How do they interact with each other? Well, the positive charge pulls on the negative charge with the force F1, and equal and opposite the negative on the positive. Let's put another charge here. Now that charge is going to push on the positive charge intermediate there, away from it, and likewise equal and opposite. Charge 2 pushes on charge 3. And then there's an interaction between these two charges, the negative and the last positive, toward each other. You see it's smaller in size because this separation is greater. Bottom line is, this of course can get very complicated, but for the net effect, each charge, you just add the vectors. So for the first one, there we have F, the resultant force vector. We could do that for all of them. And so we just have that force is equal to the summation of all the individual forces acting on that particular charge. So speaking of vectors, let's consider the way in which an electric field is really a vector field. Because at any point in space, it's got a particular value based on the distribution of charges that are affecting that region of space. If we consider an isolated charge, there we go, a positive charge and a negative charge. we see that the direction of the arrows are reversed. In fact, the field lines graphically represented here are showing the direction of force on a test charge, which we already discussed. You put a positive charge here, this is the direction of force on it. You put the positive charge here, and the direction of force is toward the negative. Shows the relative strength based on the density of the line spacing. And the lines go from positive to negative, always. But right now, these are showing isolated charges, not interacting with each other. We'll do that next. And the lines themselves also represent high potential to low potential. When we say potential, yes, we're really talking volts. So there's a higher voltage close in than further out. And we're showing interacting charges now with the little chirpy sounds, which is really what electric fields sound like. And so these are interacting with each other. See the field lines going from positive to negative. And they make big, huge loops around here. This one, theoretically, should go to infinity and then come back here, which of course it never would. But as soon as you put these two charges in proximity to each other, these loops travel outward at the speed of light. And so in 1.2 seconds, the effects of the interaction of the electric fields loops clear out to the moon. So that's pretty hard to imagine, but yet true. For point sources, the electric field is kq over r squared. This is that proportionality constant k. More precisely, considered as a vector. And so it's the same thing, but followed by the spatial vector r, the spatial unit vector. Because the direction of this magnitude is really important. It's points in some spatial direction. Now, considering other geometries, like for instance a line of charge, notice from this perspective they're going straight out from the line. If we look at a cross section, it looks similar to our isolated charge, but it's actually quite different. This is a two-dimensional slice of the three-dimensional divergence, where the field lines are actually having two dimensions of divergence as they go out in three-dimensional space. This end view is showing only the single dimension of divergence. They're diverging out in this direction as we go around the conductor, or the line of charge, I should say. But if we look horizontally, the horizontal components are all canceling. So there's no divergence along the line of charge itself in this direction. So it reduces the dimension of divergence by 1, which of course is going to change the nature of the equation specifying the electric field strength. Likewise, with a plane of charge, we have cancellation in 2 dimensions inside here. So ultimately, we just have a constant, uniform electric field between the plates. So we'll hit that again later. But just to note right now that no matter what the E-field distribution is, or its source and ultimate distribution, for all types of these E-fields associated with charge distributions, the total electric field in a particular region is just the addition of all the electric fields from the distribution of charges themselves. So this is what we call a vector sum. And that is an overview of the concept of the vector field.